Good afternoon, everyone, and welcome to the EOL seminar series. I believe that we have the first ever joint seminar with HAO, the High Altitude Observatory. The speaker who brings the two NCAR lab communities together is EOL's very own John Sobtzak. John is the senior engineer at the In-Situ sensing facility, where he is responsible for the integrated sounding system instrumentation suite, with a primary focus on developing the 449 megahertz wind profiling radar system. John holds a bachelor's in electrical engineering at North Dakota State University and a master's at the University of Colorado. Recently, John completed a certification at CU in satellite system design. Speaking of satellites, John's presentation focuses on the space side of engineering with an introductory talk on CubeSats. What are they? Why are they? And John's involvement with them through his work at CU. We are using Slido to pose questions which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Do not be alarmed if you do not view your question. We are collecting all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. John Sobtzak, we welcome you to EOL and HAO, and the virtual stage is yours.
Thanks, Jackie. Can everybody hear me? Can anybody hear me?
We can hear you, John.
Okay, good to go. So good afternoon, everyone. My name is John Sobtzak. I am the electrical engineer for the In-Situ sensing facility at NCAR's Earth Observing Lab. And today I'm talking about CubeSats. And Jackie, some people wondering why radar engineers give me a presentation on CubeSats, and Jackie mentioned it. As I was doing my master's degree over at the University of Colorado here in Boulder, I did a lot of work with CubeSats, and it led me to earning a certificate in satellite system design. And I've been working on CubeSats, when I say working, I should say volunteering with CubeSats over at the University of Colorado for almost 10 years now. Oops, let's get my slides moving. So the overview of what I'm going to talk about today, I'm just going to give a nice brief introduction to what CubeSats are. There's been a lot of talk about CubeSats in the news, and a lot of people don't know what they are. So hopefully I can fill in some of those blanks today. So I'm going to talk about what a CubeSat is and what's inside a CubeSat, and mainly that's discussing the CubeSat subsystems. I seem to have missed a line missing on my agenda. I'm going to talk about the engineering challenges of CubeSats briefly before I talk about the subsystems. And then I have several examples of the CubeSats I've worked on and some other ones I would like to show. That will make up the bulk of the presentation. There's some other considerations I put together on other slides, but I don't know if I'll have time to cover those, but we'll find out. So let's talk about what is a CubeSat. Historically, satellites have been very large. They've been the size of a car, a school bus, or very thousands of kilograms, thousands of pounds. But there's a class of satellites called small sats, which are defined to have mass of roughly less than 180 kilograms. And this is where CubeSats fall in. Small sats, the umbrella of small sats is broken up into several subcategories, if you will, based on their mass, going from a mini satellite on the large side all the way down to a femto satellite, which is very, very small. And most people don't even know femto satellites exist. I show a picture of Cornell University created a femto satellite that's just a circuit board about the size of a postage stamp. And that's actually a satellite that they flew. For the most part, CubeSats are considered nanosats because they fall into the category of nanosats because of their mass. One thing I will note that these are not hard and fast limits. So if you are 11 kilograms, you're automatically moved up to a microsat. There is some fuzz in between these lines. If you want to learn some more, the two links at the bottom are a couple of good resources. The NASA Ames Research Center link at the bottom is particularly I like. They do a lot of CubeSat work at the Ames facility. So more specifically, what makes a nanosat a CubeSat? Well, a CubeSat refers to a standardized form factor. And it comes out of a project that was started in 1999 at Cal Poly in Stanford called the CubeSat project. And what came out of that project is they created the CubeSat design specification, the CDS. which is what actually defines what a CubeSat is in terms of size. Specifically, they created what they call the CubeSat unit, or one use, which is 10 centimeters by 10 centimeters by 10 centimeters cubic, hence a CubeSat. And that's a 1 liter of volume. And they said, well, we'll let that have a mass up to 2 kilograms. And that has now evolved in the latest version of the CubeSat design specification linked at the bottom there, which is on version 14. There are now CubeSats all the way from 1U up to 12U. So when you see the sizes there, and basically what they did is they started taking the 1Us and they started stacking them. Well, that's a 2U, that's a 3U, let's put those together, that's a 6U. There are 24U satellites I've seen in design stages. I don't know if any have flown. But the big point is what they did is they formed the standard that defines what a CubeSat is. And this allowed people to develop launchers, and everything is of the same size. So everything was very standardized and makes it easier for other parts to be developed. Real quick, some engineering challenges. When you start to design CubeSat, you got to think about what the environments you're going into. And I'll start by saying spacecraft in general are divided into 2 major components. They'll call it the bus and the payload. And the payload is typically the thing you wanted to put into space, either be people or you want to put some kind of science instrument or experiment. That's the thing you actually want to study, but you need a vehicle to get it there. And that's what they call the bus. I'll mention a lot of CubeSat payloads are cameras, especially in the university. People like to take even a GoPro camera, put it on a CubeSat and take a picture of the Earth. There's radiometers to measure radio field spectrums. There's magnetometers that use it to measure the Earth's magnetic field. And a lot of CubeSats actually are used as technology demonstrations for other larger projects where they say, hey, we have a new radio or we have a new instrument. We want to try it out on a smaller scale. One thing I did not put in the slides is CubeSats are used heavily because they're relatively cheap compared to large satellites, like an order or 2 of magnitude cheaper than the big satellites. So they're very popular for that reason. My presentation is focusing mainly on the bus of the CubeSat, which is the infrastructure that provides all the services for the payload. And you can think of the bus as a school bus with a payload are the kids. But the bus, in this case, for CubeSat, you have to provide the structure, the electrical power, the communications, attitude, determination, and control. And that's what I'm going to talk about in the next section when I go into the subsystems. But one of the biggest challenges we start building CubeSat is you have to realize CubeSats in any satellite face extremely harsh environments. And they can be broken up generally into 2 environments. I like to call them, one is the launch environment, which is once you are put on the rocket, and this is how you get to space. And the hardest part about this is the incredible amount of force and vibration and shock loads put upon a satellite. Even though you're on a rocket, the forces can be quite enormous. For example, on the satellite I'm working on right now, it's going on the SLS, the Space Launch System rocket, NASA's new big rocket. One of the requirements says our satellite has to survive mechanical vibration load of up to 26.9 Gs along one of its axes. That's almost 27 times the force of gravity as it rides into space. It also has to be able to absorb sound shock waves in excess of 133 decibels, which would blow your eardrums out within a second. So it's not a smooth ride to get to space, is what I like to say. So then once you're in space, the space environment is no fun either. First of all, there's no protective atmosphere, which I think we take for granted because of all the effects the atmosphere have. First, it blocks a lot of radiation. And there's a lot of solar radiation and other radiation flying through space, and that can affect or even destroy your electronics or your sensitive instruments. So you have to keep that in mind when you design CubeSats or any satellite. The other one is there's extreme thermal conditions in outer space. If you're pointed at the sun, the side that's facing the sun could heat up to 100 or 200 degrees Fahrenheit, whereas if you face in deep space, that face could actually cool down to -40, -60 degrees Fahrenheit. So there's a large temperature extreme you have to take into consideration when you design these things. One thing to note is there's no plugins in outer space, so you have to be very aware that you have a limited power source. All the power you get from in outer space on CubeSats comes from solar panels and solar cells. And the other challenge is it's a very long distance to talk to a CubeSat over a radio. The minimum, if you're in a low Earth orbit, you're talking 400 to 500 kilometers, maybe 300 to 350 on the lower end. But if you're going out into higher orbits or deep space, you can be talking for millions of kilometers. And that's a very difficult thing to do from a CubeSat that's only the size of a shoebox. All this means is that CubeSats require very robust design methods. And in order to make something robust, you basically have two options. One, you can make it bulletproof, which means use the strongest metals, the most rad-hardy electronics, and to try to make it as strong as possible. But even those can fail. A more common approach to make something very robust is to add redundancy. Not only does redundancy add a backup, but it's much cheaper than trying to buy like high expensive rad-hardy electronics. You can fly off-the-shelf electronics, but use multiple copies for a fraction of the price. So those are some of the challenges I want you to keep in mind. I wanted to put those in your mind as we talk about what's inside a CubeSat and the subsystems that actually make up a CubeSat bus. So let's start with structures. Excuse me. So as I mentioned, the easiest way to describe the structure is its job is to hold everything else together and support everything. That's the easiest way of saying it. It's strong, heavy mechanical design. You have to survive the launch environment, which I talked about is very, very rough. And you have to survive the vacuum of space. You can't come apart once you hit a vacuum. It includes the design of any deployable mechanisms. If you have a solar array that must deploy, or a radio communication antenna you want to put out, or a piece of instrument you want to move away from the CubeSat, it all falls into the structure sub-design. One of the pieces that often gets overlooked is the interconnect paths of the wiring that has to go in. I've seen a lot of CubeSat structural models where they have all the parts in there, they're nicely modeled, but they don't have any of the wiring in place. And you go, how are you going to connect those? And they're like, oh, wait a minute. And you have to go back and you have to move some parts around. Structure design would also cover things like the center of gravity, for example, where you put things in the CubeSat so the center of gravity meets the requirements of the rocket or the launcher. There's also a thermal aspect to the structure design because the structure is usually the mechanism for radiating heat into outer space. There's no air in space, so to get heat out of the satellite, you have to radiate it, which means you have to get heat from the internal mechanism that's generating it out to the structure, out to the cold side of the structure, facing away from the sun so it can cool. So I show two examples of structures here. On the lower left is the Colorado Space Grant Consortium's All-Star bus that I worked, that's one of the satellites I worked on, I'll show later, but it's a 3U satellite, so it's 10 centimeters by 10 centimeters by 30. It uses kind of a rail structure that you can see, and what you can actually see, this is actually longer than 3U in length because it's got a telescopic, the inner part, when it deploys, extends out, so the payload's actually away from the actual rest of the bus. Contrast that with the CUE. The CUE-3s is the University of Colorado's Earth Escape Explorer, which is the satellite I currently volunteer with. It's a 6U structure. This is the structure. It starts out as a 120-pound or so block of solid aluminum that gets machined out to what you see there. And that is done for mechanical strength. There's a top plate that bolts on. You'll see some of that later. But these are a couple of flavors of structures used in CubeSats. Command and data handling and flight software, kind of the two subsystems that make up the brains of the CubeSat. Command and data handling is a little more geared toward the hardware, and the flight software is obviously software. Robust design is very important on these two systems because if you have no brain, your CubeSat's a flying brick is the terminology I like to use. One of the biggest things with the electronics due to the radiation in space is they call them single event upset faults, which is basically you have a transistor that gets hit by a radiation dose and it flips its state from on to off. So the bit goes from a 0 to a 1. And now you have a corrupt memory location, a corrupt instruction in your program, whatever. So to help guard against that, you can put some mechanical shielding around the electronics, which is somewhat effective. It's aluminum and steel are okay. You really need a heavy metal to block some of the particles. It is used though. One of the biggest things to do is to use fault tolerant software. So when you program the thing, you make the software capable of detecting these single event faults and say, oh, there's something wrong here, and let me go fix it. And a lot of this is done with both redundancy and hardware and software. You'll fly, the CubeSat could have two computers that keep checking with each other, and the software is always, you have multiple copies of the software stored on flash drives. It's just a lot of redundancy in this system. As for the hardware, up in the upper right, I show a BAE Systems RAD hardened flight computer, which is, it's 10 centimeters on edge, so it'll fit into a 3U. That flight computer probably runs several $1,000s. It's very expensive. And I will say at the university and high school level, the hardware for command and data handling can be as simple as a Raspberry Pi or a BeagleBone system on a card. They're very common used. A couple of satellites I worked on used Raspberry Pi. Another one used a BeagleBone Black for its attitude determination control subsystem. And then when you talk about the software, you have to figure out what architecture you want to use. Do you want to have an operating system on board? Do you just want to have straight up embedded system coding? If you're collecting data, do you want to do any single processing on board, like averaging or filtering? That would be done at the, if it's not done at the payload, it would be done at the command and data handling subsystem. And one of the big ones is, how much autonomy does the CubeSat need? In other words, is it going to do things on its own and detect certain events? If it goes into the shade, will it turn things off? Or is it only going to respond to commands from the ground? And that's always a trade-off when it comes to programming. EPS, the electrical power system, is, we've got a few requirements. First of all, it's, as one can imagine, it's responsible for generating the power that the CubeSat needs. And that is done through solar cells and solar arrays on CubeSats. Off on the right-hand side, you see the solar cell array that's going on the side of the CUE cube. That's a 3U solar cell array. One of the big questions you must ask is, how big of an array do I need when you're designing the EPS system? How many solar cells do I have? How efficient are they? Assume they will not always be pointed into the sun at a right angle. And then there's also redundancy. What happens if a solar array goes down? Do I still have enough power? Second job of EPS is to distribute that power to the rest of the bus and to the payload. And the electronics of the bus and the payload both like constant voltages. So you have the voltage regulators are in there. Load switches are used to turn power off to different parts of the subsystem or to the payload. A lot of times a satellite, a CubeSat, cannot run all systems at the same time because it consumes too much power. It consumes more power than it can be generated. So you got to turn this on and turn this part off and so on and so forth. One of the big parts is you're always monitoring the current and voltages on all your power systems, all the subsystems, in case something, you're looking for a fault, you're looking for, if something gets hit by radiation, does it short circuit, and then you can turn it off. Third job of EPS is you have to store power. And this is basically, if you're orbiting the Earth, you're going to go around the backside of the Earth, and you're going to be away from out of the sunlight, and you're not going to have any power supply. So CubeSats use lithium-ion batteries like everything else these days. One of the big questions is, how big of the battery storage do you need? How many battery cells? The power storage also includes the charge controller for charging the battery systems. You just can't apply a voltage to lithium-ion batteries. They like to be charged a certain way. In the same vein, they also have a peak power tracker. So when you draw power out of the batteries, you're doing it in a way that the lithium batteries can handle it. You're not trying to draw massive amounts of current at once. Typically, you have a power budget, which is a simple spreadsheet to says how much each subsystem needs and how much power I can generate. And you want to be what they call power positive. Power positive means you're generating more power than you are using, so you can charge the batteries up, etc. The battery pack on the lower right is a 60 watt-hour battery pack from Tyvek. It's got 6 cells, and the black circuit board on the top would actually probably contains the battery charger and the peak power tracker, and probably some monitoring circuit as well. Attitude, determination, and control system, guidance and navigation, also known as guidance and navigation. excuse me. So you're flying around in outer space, either around the Earth or out in deep space, and you need to know where you are. And that's the purpose of this subsystem. It's to determine where you are and which way you are pointing. That's the attitude of the CubeSat. Some instruments that are commonly used, a star tracker, which is that camera thing you see there on the right, takes a picture of the star constellations and compares it to a database it has loaded on board in the computer, often in the CDNH subsystem. And by figuring out which stars are where, it can tell you which way you're pointed. Another way is to use sun sensors, which on the far right is a pyramid structure of a sun sensor. These are just like photo detectors. They help you figure out where the sun is. This is very important. For example, if your batteries are getting low and you need to charge up, you want to know where the sun is so you can turn your solar arrays into the sun. If you're in low Earth orbit, you can use magnetometers along with the Earth's magnetic field to help you figure out which way you're orientated. And a lot of satellites that go into low Earth orbit or use GPS systems. They use unlocked GPS to help figure out where they are. So once you figure out where you are, you have to ask yourself, okay, where do I want to be? What attitude do I want to be in? And there's algorithms and modeling used to help determine that. And then from there, you figure out how much roll, yaw, pitch, or delta V acceleration you need to get to where you want to go. And then there's the control mechanisms. These are the things that will actually turn the spacecraft or move them. Magnetorquers, which is on the lower left, are simply just coils of wire. And they're just magnets. And they're flown on low Earth orbit satellites that go around the Earth, because when you apply a magnetic field on the magnetorquers, it interacts with the magnetic field of the Earth and puts a torque on the spacecraft. Just like two magnets, if you bring two magnets next to each other, the same polarization, they'll push away or attract to each other. There's actually three magnets on that magnetorquer, and they're wound in orthogonal directions. So you have 3-axis control. There's one wound this way, the other one's this way. The third one is around the square. A very popular way to help turn a satellite, adjust the attitude, is called reaction wheels. And this is a simple physics. If you go back to, I learned it in junior high school physics, if you sit on a stool and you put a bicycle wheel over your head, you spin the wheel one way, you turn the other way. It's the equal and opposite reaction of rotation. So these little reaction wheels are very small. They're only about that big, that square. And you put them on the satellite in three orthogonal axes. And if you want to turn the spacecraft one way, you accelerate the wheel. If you want to go back, you accelerate the wheel the other way. The only problem with reaction wheels is if you have some kind of external force like drag, and you're constantly having to correct with a reaction wheel, correct the attitude, the reaction wheel is going to go faster and faster and faster. And at some point, it can't go any faster. And they call that saturation. So then you need another force to counteract the wheel to slow the wheel down. Otherwise, you'll spin back the other way. So for satellites, CubeSats in low Earth orbit, they often have magnetorquers and reaction wheels on it. So when the reaction wheels can turn the spacecraft much quicker because they have a lot more torque. And then when you get a chance, you can use a magnetorquer as an opposite force to slow the wheel back down. So they combine together to give you a nice attitude attitude control. The other piece of the pie is propulsion, which is its own subsystems. That's basically once you get orientated, your attitude the right way, you can light up a rocket engine and get you sped up to where you need to be. So from that, I actually go right into propulsion. I will say propulsion is not used on many CubeSats simply because they don't need it. Unless they're going out to deep space. If most CubeSats are in low Earth orbit, they can use magnetorquers or reaction wheels. However, they can use a low thrust propulsion to help them keep their attitude as well. Lots of different types of propulsion out there. As simple as cold gas, which is you could compress nitrogen, for example, and then just spray that out, kind of like and use that as a thrust mechanism. Monopropellant, hydrazine is very common, where hydrazine's a fluid that when you run it through the catalyst that's inside the nozzle, it ignites. And then bipropellant, which most people will know is like a fuel and an oxidizer. For example, the space shuttle used hydrogen and oxygen and as its fuel and oxidizer. The thruster there on the right is from Dawn Aerospace. It uses nitrous oxide, and I think it's propene C3H6. There's a lot of research these days in CubeSats on electric propulsion and ion propulsion, mainly because they're low thrust, they're small, they're lightweight. You don't have to carry a lot of fluid with you. And CubeSats themselves, like I said, don't need a lot of thrust. JPL had if you go to NASA and just Google electric thrusters for CubeSats, they had a whole web page. And I just pulled an example of one from their next ion thruster. And that thing's only about that big around, so it can be used on a CubeSat nicely. The communication subsystem, sometimes people will call it telecom. Some other people refer to it as tracking, telemetry, and control, or TTNC. This is basically how you talk to your satellite from the ground. This is how you command it. This is how you get data back from it. There's two pieces. The terminology uplink is the command and control, where you're sending commands up to the satellite. And then the downlink is known as telemetry. That's where you're getting the status of the CubeSat. What's the system? What's the temperature? What's the battery voltage? And then any instrument payload data will come down through the telemetry link as well. Cube satellites, like a lot of satellites, use radio communications primarily, and they use frequencies from VHF all the way up through microwave. The antennas that they use themselves can be a fixed antenna, or they can be conformal, meaning they're on the side of the spacecraft, so they actually form like a wall. And deployables are a big thing. If you look at the upper right, one of the most common CubeSat satellite antennas you will see is made out of a tape measure. It's a very easy, low-cost antenna. You go down to the hardware store, buy yourself a tape measure, cut it to the appropriate length, hook it up, and then you can wind it up like a tape measure does inside the CubeSat, have a little release mechanism. And once you get ejected, it springs out and you have a simple monopole antenna. Because CubeSats are so small and they don't have a lot of power generation or large antennas arrays, it's very helpful on the comm side if you have a large antenna on the ground station side to help close the link. I will say there is a lot of research in antenna technology going on, both for CubeSats, satellites, and just about anything, especially with 5G coming online. One of the technologies that we're going to demonstrate on CUBE is there's a feed horn antenna on the lower right. It's a feed horn antenna has been around for a long time. The thing with that particular feed horn antenna is that it's been 3D printed. I don't know if you can see it in the image, but it's got a rust surface. So one of the things we're going to show is if a 3D printed feed horn works, if it provides another way of manufacturing some antennas. Some of the big research is in optical communications. People want to get a lot of data from their satellite downlinked. Downlink is by far the largest demand on communication. So there's a lot of work on high-speed downlinks using optical laser technology. One of the things you'll need when you design your CubeSat is you're going to have to do a lot of link budget analysis to determine the capabilities. And this will tell you how much data can I get down using this antenna, how much power do I need on my transmitter, which then feeds back into how much power do I need from EPS and how much heat am I going to generate. It's all interconnected, but the link budget analysis really comes in handy to help you figure that out. Thermal. Sometimes it's separate subsystem. Sometimes you'll just have a thermal engineer that goes around to different subsystems. It's often overlooked. The thermal subsystem has to interact with other subsystems very heavily to determine what they need for heating and cooling effects in the CubeSat. And the goal of the thermal subsystem is to make sure that all the components in your satellite stay within the specified storage and operating temperatures. In particular is the batteries. The battery, lithium-ion batteries do not like getting very cold, so you'll have some kind of heating element on them to keep them warm if they're facing away from the sun. Cooling, one of the big things that need to be cool are electronics. The image on the right is a picture of the All-Star Thea satellites radio frequency radio board. And I'll tell you the hot spot that's highlighted is the transmitter power amplifier. It was much hotter. So we had to get the heat from that chip out to the structure and so it could radiate into space. And what we wound up doing was I had a mechanical engineer and the thermal guy machine a piece of copper that was about 1 millimeter or 2 millimeters thick that on the back of the circuit board, we soldered the circuit board to the circuit board and provided a nice low thermal resistance path to get the heat out to the rails. And it worked very well. So heating thermal control can be passive or active. Passive would be similar to that piece of copper where you just give it a nice thermal path. You put, if you want to keep something warm, you can give it a thermal blanket. There's active, which is things like active heating, which is a heater element. The biggest source of heat, if you really want it, is the sun. If you can use the sun's energy to keep you thermally the way you want, life is a lot easier, and then you don't have to waste energy on heating elements, for example. Cooling, as I mentioned before, the only way to cool is to get the heat to the structure and to radiate into space. There's no conduction, there's no convection. Radiation is the only methodology. I will mention a barbecue roll. Often you see things in space, both in videos, or they have a slow rotation to them. And I thought barbecue roll was something somebody just recently made up, but it's actually terminology that goes back to the 60s. If you have the sun on one side, if you rotate the satellite or your flight object very slowly, it'll heat and cool. It keeps it at a uniform temperature, and it's a very common way to passively keep thermal control on your CubeSat. The hard part is if you have to stop the barbecue roll because you have to point a certain direction for either communicating or instrument. The systems engineering role. The systems engineer role is mainly responsible for defining what the requirements for the CubeSat need to be, what the CubeSat needs to do from a customer's point of view, or from the customer's requirements and other external entities like, well, what's the launch vehicle requirements? What's the deployer requirements? As a result, it flows down requirements for the other subsystems I talked about based on those high level. And the way they do that, they use these things called interface control documents, which define where one subsystem ends and where the other subsystem starts. And more importantly, it defines the interface between them. Like, for example, what's the power voltage going from EPS to the command and data handling? What's the data line? Is it an Ethernet? Is it a space wire? The image I put up here kind of gives you a nice example of a system view of a satellite. I did this as part of my satellite engineering class. And I have the structure surrounding everything because the structure has to hold everything. And then the individual subsystems, energy, electrical power system has the solar arrays, has the batteries, for example. It has some thermal management system that is controlled by the main thermal subsystem over here. The communication had multiple transmit and receive antennas, and we had a laser communication demonstrator on board. Propulsion, we had some thrusters to help keep us orientated, and some main thrusters to get us out. This particular satellite was designed to go to Mars, so we needed a propulsion system. Command and data handling, for example, had A and B are two of the computers. There was redundancy, and 2 disk drives, completely redundant to make it a robust design. Then the attitude determination control system had reaction wheels and magnetorquers. I'm sorry, not reaction wheels. I don't remember what those are. They're not magnetorquers because we're going to deep space. But the big part of the systems role is to define all this wiring in between in the interface and how everything talks to each other. Okay, let's look at some examples. Probably one of the most well-known CubeSat in recent years, because it got a lot of press, is called Marco. These are a set of twin 6U satellites that were designed at JPL, and they were sent to Mars along with the In-Situ lander project. And basically, they provided radio relay links to the In-Situ lander as it descended into the Martian atmosphere. The image over on the right, you can kind of see the descent lander here, and then the 2 satellites would pick up the signal from the In-Situ as it went through the atmosphere, and then relay data back through clean space to the Earth. So now you're looking at sending a signal many millions of kilometers from something the size of a shoebox. So one of the innovations they were the first to fly this high gain reflector array antenna. which helped them focus the beam and get enough gain to get the signal back to Earth so it could be detected. So down here at the bottom, there are a couple of images of what the satellite had. You have UHF antenna, probably for communicating, with the InSight lander. There's a patch antenna on the end. The solar arrays, which are gimbaled so they could turn, that allowed them to point the solar arrays at the sun or as close as possible while pointing the reflector array back at Earth. Here's an image you can find online of one of the Marco satellites. I don't know if it's A or B, but you have all the solar cells for generating the power. You have a patch antenna for communications. You have a thermal blanket to help with thermal, the giant reflector array, and you can see there's hinges on this thing because this whole thing had to fold up into a 6U size shoebox size deployer. So the two sides of the reflector array fold in, and then it folds down. Same with the solar arrays, they fold up and they mounted on the sides. So a lot of mechanical design in this work. On this little black dot right here, if you can see my mouse, is a camera. And the square patch over here, the aluminum, is the feed element for the reflector array. So it would actually send a radio beam from here. It bounces off the reflector array, hence the term reflect, and it refocuses the beam for a higher gain. So this lets you get a higher gain antenna in a smaller package. This is one of the more, one of the more known pictures taken from Marco. They took this picture as a test, and that camera on the center, you can see part of the thermal blanket. You can see the high gain feed antenna on the left and the reflector array on the right. And what's really fun is you can see the Earth and the moon. So this thing was on its way to Mars, and they turned the satellite and took a picture of the Earth and moon. So able to do this from a 6U satellite is pretty challenging and pretty neat that they were able to do it. One of the other images they were able to take after they completed their landing is as one of the Marcos flew by Mars, it was able to capture this image of the Martian planet as it flew by and radio it back again. Very, very hard to do from something that's only, starts out as a shoebox. It doesn't have a lot of power generation. It doesn't have a super high powerful radio to send the signal back, but they were able to do it. What am I doing? There are a lot of commercial companies that have popped up in the last 10, 15 years doing small sats simply because of the CubeSat definition has made it economical. And the technology is now shrunk down where they can fit into a small sat form factor. One of the examples is Planet Labs, and they fly what they call a constellation of small sats, a CubeSat constellation. Similar to how GPS is a constellation of satellites, but they're further out. Planet Labs flies these things called doves. They're 3U CubeSats, so they're 30 centimeters by 10 by 10 centimeters. And they use them to image the Earth. They fly them. You can see in the top image, there's a camera lens at the end. And when the thing pops open, here's the radio antenna for radioing them back. It's got some solar cells, and these panels coming out the side are also solar arrays. And they use these things to take pictures of the Earth. The trouble is they're in low Earth orbit, so they fall out of orbit and they burn up every so often. So they keep having to replenish the constellation. So they launch new satellites every 3 to 4 months. And so far, according to their website, they've collected over 7 petabytes of imagery using these CubeSats. So that's one of the big uses of CubeSats is taking pictures of the Earth. All right. Now we move into ALSAR. This was my first CubeSat that I volunteered with over at the University of Colorado. This is a project over at the University of Colorado Space Grant Consortium, or Colorado Space Grant Consortium, which is located in the Engineering Center over in at CU's campus. ALSTAR stands for Agile Low-Cost Laboratory for Space Technology Acceleration and Research. In this case, ALSTAR is the bus and THEA is the payload. The THEA was the telescopic high-definition Earth imaging apparatus. It's a camera. This launched I started working on this project in, I think, late 2011, or August 2011, until it launched on April 18th in 2014 on a Falcon 9. In the images on the bottom, the lower left, on the far left over here, that's the camera. There are reaction wheels and torque rods inside, magnetorquers inside this casing to help turn it. This camera right here in the middle is a star tracker to help determine attitude. You see the battery pack. And one of these two sets of boards, I don't remember which one, is the radio. There's a digital comm board and a RF board, which I did. I have that pictured off to the right. That's my first satellite radio I ever put together. X-band, UHF uplink and a S-band downlink. The thing was launched on the Falcon 9. It was deployed. Our ground station was a dish antenna that's located about 15 miles north of Boulder on a ranch. And it picked up, in one of the passes, we were supposed to be transmitting at 2.4017 megahertz. And lo and behold, we picked up a blip. And that's all we ever heard from the satellite. We never were able to establish contact, and it fell out of orbit on Memorial Day. The follow-up to All-Star Theater was All-Star Polar Cube. Polar Cube is a radiometer project with collaboration with the Center for Environmental Technologies and the National Snow and Ice Center data center. It uses a miniaturized microwave radiometer that's passively detecting 118.75 gigahertz. It's looking for diatomic oxygen emissions on that spectral line. I just found out about 2 hours ago that this launched a couple of weeks ago. You may have seen in the news that Virgin Orbit launched it. Here's an image in the lower right that shows Virgin Orbit 747. If they drop a rocket and it launches it in space, Polar Cube was on that rocket. And I did not know that until just a couple hours ago. I got an email update this morning that says they were able to detect a radio beacon from it, but they were not able to decode the packets yet. So they're still working on it. But the Polar Cube was part of the Alana project, which is education launch initiatives for nanosats. I believe it's a NASA program. And then also they were part of, there's another program called UNP, the University Nanosat Program, which is run out of the Air Force, runs that out of the Air Force Research Lab, I believe. That provides funding and launch opportunities for satellites built by college people. But in the satellite, you see you got the radiometers up top here, the reflector dishes to help collect data. For those of you in EOL's remote sensing facility that knew Bernard Wang, he helped design this reflector when he worked for Dr. Alban Gaszewski over at the university. I believe this is a reaction wheel assembly in the middle. There's a UHF antenna off the back orientated in such a way as to minimize any interference with the radiometer, even though they're extreme opposite frequencies. And the rest of the bus is included. Now we get to CUE Cube, and this is the project I have been working on now for almost 5 years, volunteering with over at the University's Aerospace Engineering, University of Colorado's Aerospace Engineering Department. This is a project that comes out of NASA's CubeQuest Challenge. NASA's CubeQuest Challenge is part of their Centennial Challenges program, where they put out different challenges where people can submit designs and win money. Or in this case, we won a slot on the NASA's SLS Space Launch System rocket that's going to take us out to deep space. The challenge for us in the Deep Space Derby is error-free digital radio communications from 3 million kilometers and beyond. So what's going to happen is the Artemis I mission, which is the maiden launch of the rocket, I have a video I can show you here in a minute. It's going to take the Orion spacecraft, which is the new Apollo, that's going to go around the moon, and then the upper stage is going to fire up again and take us out to deep space, and then we'll be ejected. We're going to be ejected before we get to the moon on a trajectory that's going to take us to deep space. And we're going to try to communicate with it. And once we hit 3 million kilometers, the competition starts. We have a C-band uplink, which is supposed to be a patch antenna. It's not shown here, right there. And then we have 2 of those X-band feed horns. One is used as a feed element off our reflector array, and the other one's as a backup, a secondary. The feed horn and the reflector array were both designed by a PhD student at CU named Ellie. He did a wonderful job with them. We took them to an anechoic chamber. and it worked just marvelously once we put a ground plane on the reflector array, of course. Give you an idea what's in the system. This is the block diagram. Our main computer, attitude determination controls up here with the reaction wheels, the star camera, the flight computer, the battery pack, the solar cells are off to the sides. We have the electronics for the receiver, the transmitters up over here, and then we have a board in the middle to help connect it all together. And I will say even the simplest satellites are very complex. On this particular satellite, I was brought in, I started as a volunteer in the communication system. Then I was the head of the comm subsystem, and then I did some of the system engineering for a while. And now I'm the chief engineer for the project. So I help oversee all the circuits, the electronics design, and mechanical design, which is done. And one of my favorite images, I always have to show this one, is the wiring diagram I created for the satellite, because even the simplest satellite is very complex. It is about 470 connections between all the components. I'll mention T-Miles real quick before I get to the video, and then I'll pause for question. T-Miles is a group of citizens that won a spot with their entry onto the Deep Space Derby. They're our competition. And a couple of things notable about their satellite CubeSat is they developed their own plasma thruster. And there's a picture of it being tested on there. The other thing is they're flying autonomously. They don't have any command uplink. So once they get ejected, they're completely autonomous on their own. So yeah, it could be a good competition. And now I just want to show a video. This will show you kind of what's going on at Artemis I and the CubeSats. Some of it, it's from NASA, and some of it is a little advertising-ish, if you will. But let me mute my microphone.
NASA is advancing science and technology with the first flight of the Space Launch System, or SLS. Demonstrating the capability of the new rocket and the Orion spacecraft in deep space for future human exploration is the primary goal of the mission. As a bonus, SLS will send small satellites called CubeSats to deep space destinations where they can gather valuable data for future exploration missions. Once in orbit, the SLS upper stage, called the Interim Cryogenic Propulsion Stage, fires its engine to propel Orion toward the Moon. SLS will send Orion farther out beyond the Moon than the Apollo astronauts traveled, where it can test communication, navigation, and other deep space exploration systems. Once Orion is a safe distance away, the fleet of 13 CubeSats will be deployed. The onboard avionics box will command each dispenser to release the small satellites, sending each one on their way to deep space destinations such as the Moon or an asteroid. Each has a mission that can provide NASA with new key knowledge and test new technologies. CubeSats flown on the mission will perform in-space experiments and demonstrations that will actively advance the capabilities needed to take humans farther into space than ever before.
So that's the CubeSat CubeCube is one, and T-Miles are two of the ones that will be on that rocket. And I'm going to stop there, Jackie, if you're listening. I will say there's a new video NASA put out on the same one. Here's a link to it on the slide. Whoops, let me get my slides back up. There we go. If you want to go, this link, it's a similar video talking about the SLS, and it highlights a CubeSat called Mia Scout, which is Near Earth Asteroid. It's a 6U CubeSat that's going to use a solar sail to go look at a nearby asteroid. So it's going to use a solar sail and solar radiation pressure to try to go and catch up with an asteroid. Jackie, I'll send it over to you then.
Great. Thank you, John, for a really great introduction to CubeSats. I didn't know that CubeSats were a class of small sats and that there were satellites the size of a postage stamp. What do you measure or record on a satellite that tiny?
A lot of those, I think, are just transponders. They're just radio communication transponders, or they might be picking up on magnetic field strength or something like that. There's not a lot you can put on a postage stamp. There's not a lot of power you can generate from a postage stamp. That's the hard part.
Well, we have time for questions, and I see a few people have already started asking questions. Again, please use the Slido interface, which is below the presentation screen. We have a question from Eric Johnson. How often do CubeSats typically experience single event upsets?
I don't know off the top of my head if there's a commonality. A lot of it is dependent on solar flare activity, actually. And if you are in LEO versus high altitude orbit, or if you're out in deep space, you're more exposed. A lot of LEO satellites, they'll fly and not have a single interrupt, even just using commercial off the shelf. One of the other satellites that the Space Grant Consortium flew before All-Star was called Dandy. It was a very large small satellite, about the size of a beach ball. And it was put into a very highly elliptical orbit. So it would come around the Earth and then go way out like 600 kilometers. And it happened to be way out during a solar storm, and they never heard from it after that solar storm hit. So it destroyed their electronics. But I'm sure in the literature, they probably have some statistics on how often they occur. They could occur every day. If there's a lot of activity, they could occur once in a month, once in a year. I do not know the exact statistics.
Great. Thanks, Eric. We have a question from Miles. I wonder if this is related to Team Miles that you spoke of, John. This person says, very interesting, thank you. Do most CubeSats use parity bytes? If so, how many?
Absolutely.
Are self-correcting codes used as well? Example, Hamming code.
Absolutely. They use, even just on the shortest interconnect between subsystems, they'll use parity bits and other encoding schemes. They might use a single bit. They could use 2 bits. They use one of the bigger ones in communications is a half-rate convolutional encoding, where actually half the bits are literally correction bits. And that's used mainly for the long-distance communication. But yeah, they use a lot of parity bits, even just to communicate between subsystems, or even from the CDH going to checking its RAM to make sure, or checking its program memory to make sure they don't have bit flips. They're used everywhere.
Great. Thanks, Miles. Thanks, John. Oh, we have a question from ISF's Chris Roden. Hi, Chris. If you design for 27 Gs, what is your safety factor? What are the max Gs actually expected during launch?
So then you get into the wonderful world of acceptance testing versus qualification testing. So the acceptance levels are much lower. I think they're around 19 Gs, but they want us to shake it, I think, up to 27 Gs as a safety factor, the qualification to qualify it for launch. I'd have to check the SLS, requirements, but I think they're expecting upwards of 15 to 20 Gs in the launch, in the launch vehicle would be my guess, based on what those two numbers, the acceptance levels versus the qualification levels. So yeah, there's a pretty good safety factor when they put in the qualification levels. They give you a nice safety factor. A conservative estimate is you always want 20 to 30% of margin on a lot of your requirements to start with, and some of those can be dwindled the more you learn. Others will just keep going.
Great. Thanks, Chris. Thanks, John. Actually, I have a follow-on question from Chris's question. Where do you or can you test CubeSats that simulate a space environment or temperature gradients
Yes.
at launch?
Yes, there's a couple, my roommate's coming home, so there's a couple ways for the Vive. They make these Vive tables that you bolt the CubeSat down to the Vive table and it shakes it. It's actually a speaker. It's actually a very powerful speaker that uses magnetic fields to shake it. And then you can mount it. Some can do all 3 axes. Otherwise, you take it off and you rotate your CubeSat and you shake it that way. Team Miles, as a humorous side note, they don't have their own Vive table. So what they did is they took their satellite down to Home Depot and put it in a paint shaker to do an initial test to see how it survived. But to mimic space, there's temperature vacuum chambers, which are very expensive, where you put your CubeSat in this and then you pump all the atmosphere out to a vacuum. And then there's heaters and coolers in the system that will heat and cool through radiative properties the CubeSat in a vacuum to mimic the space environment. And that's actually required testing before we launch.
Great, thanks, John. Sorry if you hear hammering in the background, they're doing construction outside my home. We have a question from Jürgen Jensen. Very interesting work. Even if you are mainly working on the bus infrastructure, do you have any good ideas for instrumentation packages that can aid EOL's more earthly goals? Any wild ideas?
You can use, there's all kinds of Earth observing technologies that people are looking at putting on CubeSats. From, I mentioned the radiometers, magnetometers. Believe it or not, HAO has a proposal that I was trying to avoid mentioning, but they wrote a proposal to measure winds from I think it's a 6U CubeSat. I know the people over there. Nicole Ela is the system engineer, is the name I remember. She worked with me at Space Grant on the All-Star, but you can use lasers. There's a lot of CubeSats that use radar systems for measuring winds, profiles, humidity profiles, cloud densities, all kinds of stuff. If you can get it shrunk down to the size of a CubeSat so you can put it on a CubeSat, it will be used.
Thanks, Jürgen.
There's actually a lot of potential for the HAO, I think, since they measure the sun, CubeSats for use in measuring the upper atmosphere, but they also use them to probe all the way down to the ocean. They actually use reflections off of ocean as well to measure surface winds.
Cool. We have a question from RSF's Tammy Weckworth. Thanks, John. This was very interesting and informative. These are such cool projects to do in your spare time. What happens after the end of life of CubeSats in orbit? Do they fall out of orbit and burn up completely, or do they contribute to space junk?
That's actually one of the goals of some of the small sat. There's rules that say you must deorbit. You can't be on orbit more than 25 years. However, a lot of the CubeSats are launched below the space station, and they'll orbit maybe a year to 2 years. Most of the CubeSats burn up in the atmosphere. They burn up almost completely. The one exception I know on All-Star Thea, we had a piece of INVAR metal that held our optical lens. And because that has such a high thermal properties, it could possibly survive re-entry. So we had to actually carry insurance on the orbital debris insurance in case that piece of metal survived re-entry and hit somebody's house. There are very strict rules, international treaty rules. You cannot crash into the moon on purpose. You cannot crash into Mars. They call it the planetary protection rules. A lot of international contracts. So they really do try to limit space junk, and most CubeSats deorbit within a couple of years if they're below in LEO. Actually, that's one of the applications of CubeSats I've seen at the conferences. Some people come up with ideas of how to use CubeSats to clean up space junk produced from back in the 50s and 60s, like little bolts flying. I've seen a couple of proposals on that. So, but the whole purpose of the small sat and CubeSats is to not add to the space junk problem. The deep space ones, for example, Marco, they flew past, they're gone. They're past Mars somewhere. They might wind up in the sun at some point in time. CUE cubed is orbiting in Earth's orbit's in a heliocentric orbit. I do not know where that's going to end up in long term. It could eventually fall into the sun, but that's probably going to take some time.
Great. Thanks, John. Great question, Tammy. We have a question from ISF's very own Terry. Terry Hoke, what is the required testing on the ground to verify the thermal properties?
That's usually done in TVAC. Which thermal properties are you talking about, Terry? If you could give more details. You put the thing in even before you put in a thermal vacuum, you put it in a thermal chamber with an atmosphere, and you run it up to very high temperature and very cold and high and cold, and you have the wires coming out of the temp chamber on the side, and you turn the system on and off, and you test the system over temperature extremes. You do that mainly in a temp chamber that has an atmosphere, because it's easier to heat and cool things when there's air in the chamber, when you can use air. The hard part with testing anything in a chamber is testing the radio, because you don't want to transmit inside of a chamber. They often put things over the antennas called, we were just talking about this yesterday, hoods of some kind. But yeah, there's testing requirements. Our test plans usually say, put it in a thermal chamber, heat it up to 60 degrees Celsius, turn it on, check out the systems, hold it there for an hour, cool it to minus 50 degrees Celsius, turn it on, make sure it works, and things like that. If that's what you're getting at.
John, Terry's follow-on response he's asking about the radiation difference between the sun side and the shade side.
Well, the sun side's going to absorb radiation. The cold side's going to emit radiation. There are certain coatings you put on a satellite. Either there's a tape with a foil increase, or you paint it a certain color, or you anodize it a certain way to either increase or decrease the emissivity of the surface. So it either makes it easier to get rid of waste heat, or it makes it easier to absorb heat. There's extreme temperature differences. Radiation. When you say radiation difference, yeah, it's kind of hard to radiate toward the sun. I don't know if you'd be able to radiate more than you would absorb. Let's put it that way. It might be a losing battle in that way.
Thanks, Terry. We have a question from Holger Vimmel. How much, which is a follow-on question, which you may have answered when Tammy asked about space debris, but he's asking, how much do CubeSats contribute to the crowding of orbits and increase the risk of generating dangerous amounts of space debris? Are they centrally tracked, and can they perform avoidance maneuvers?
I talked a little bit about the space debris, and that they don't contribute to space debris. They're in their own orbits. There's little risk. They try to make sure they're all separated, and they do fall out of orbit pretty fast, so they're not up there very long. They are centrally tracked. NORAD tracks everything in space. Can they avoid performance maneuvers? Not really, because most of the stuff in orbits, the lower Earth orbits, don't have propulsion on board. They can only turn themselves. They can't accelerate out of the way. Once they're put into an orbit, they're in that orbit. So they can't really do avoidance maneuvers. There's a lot of, I know NASA, they like to keep a lot of the CubeSats in LEO below the space station for that particular reason. So because they have no propulsion, they can only fall downward into the Earth's atmosphere. They can't go up into higher, they can't hit the space station, is basically what they're trying to avoid. It is going to get crowded in some of these orbits. There's a lot of papers at the conferences about trying to figure out algorithms of how do we put these things into separate orbits so they don't collide with each other. You can space them out both in altitude and inclinations. I know. One thing I will mention is the CubeSat explosion of CubeSat has created new launch platforms specifically for small satellites. One of them is Virgin Orbit that I mentioned that launched Polar Cube. One of them is called in New Zealand is it's in my slides, the extra slides. I forgot their name. Electron is their rocket, but it opens up the ability to put things in more orbits, more variety of orbits than the classical big rockets, because the big rockets were typically used to go up to the space station, for example. So that very limits what orbits you can get put into. Now, that, especially like Virgin Orbit, that's their whole deal, is they can launch from anywhere in the world from underneath the wing of a 747. So they can opens up a whole world of what other orbits can we go into. So hopefully that'll help spread things out.
Great, thanks, John. We have a question from Scott Sewell. Very interesting overview, John, thanks. Has there been any scientific payload development interest from within EOL or other UCAR NCAR divisions? It would be very exciting to see an internally developed payload. HAO has a couple of proposals in the works, but I'd love to hear of other ideas.
I don't know of anything in EOL, no interest in EOL. This might spur some interest. HAO would be the kind of the big central location simply because of the nature of their work. And like you said, they do have a couple of proposals. I helped review one of them. I read through it for them. Yeah, internally developed payload. If anybody has any ideas, we'd love to hear it. If you have an idea for EOL, since EOL mainly, my understanding EOL deals mainly with the lower and mid atmosphere. There's definitely possibilities to measure wind profiles, vapor profiles, water profiles, temperature, of course, with onboard radar systems, even lasers, LiDAR systems would be of interest.
Thanks for that, Scott. Maybe get in touch with John and put some heads together. And I think we have one final, not a question, but a comment. And the mystery is solved. Miles is no relation to Team Miles, but he likes the name, so thanks again. And with that, we are past the hour of our seminar. If you are interested in this topic and have further questions, please reach out to John via his email, which is provided in the seminar flyer and on his presentation. On behalf of EOL and HAO, I would like to thank John Sobtzak on his excellent presentation about CubeSats. Thank you, everyone, and have a great day.
Thanks a lot.